Very much, everybody, for joining us. My name is Mike Long. I'm from the School of Civil Engineering in UCD and iCRAG. And together with Aoife there, I'm going to give you a brief overview of the Geohazards and Geoengineering research in iCRAG. So who are we? Well, we're a large group of researchers, as you can see there on the left-hand side, spread across 6 institutions across the country. And we're looking at more or less, I think, all geohazard and geoengineering issues, such as landslides, peat, karst, geophysics, site investigation techniques, and other similar topics, as you can see there. So what are we about? Well, our three main principles, or our 3 main aims, are to identify, monitor, and mitigate geohazards to protect society, to research the geological causes of and the controls on geohazards to address risk, and also finally to develop technologies to support geotechnical engineering. So I'm going to have a look at all of those 3 and give some examples of all of those 3. Starting with identifying and monitoring geohazards. And I should say at this stage, we're very grateful to our sponsors and our industry partners. They're listed they're on the screen there and in the subsequent slides. I'm not going to go through them in detail, but we're obviously really grateful for their support. So in a few minutes, you're going to hear a presentation by Eileen McCarthy of UCC on Upland peat stability. And this topic has been brought to light in the last year by 3 large slides which occurred in Ireland, which Eileen will address. You're also going to hear a talk from Zili Li, also from UCC. And Zili is going to be talking about big data acquisition and machine learning and how that is applied to underground infrastructure. And Zili is going to base his talk around 2 tunnels, the CERN tunnel in Geneva and the Dublin Port tunnel. Moving on to issues of developing technologies to support geotechnical engineering. These are 2 talks again you're going to hear in the next half an hour or so. Andy Trafford is going to talk about using optic fibre techniques for the purpose of characterizing the seabed sediments for the purposes of engineering design. And Dave Igoe of Trinity is going to talk about offshore foundation design, and he's got a particular expertise in pile foundation design. And Maria Judge is also going to talk on the same topic of developing technology to support geotechnical engineering. And Maria is going to briefly describe our Centre to Centre US-Ireland project. And here we're working with Queen's and 3 American universities who are part of the CBBG, the Centre for Bioremediated and Bio-Inspired Geotechnics, Georgia Tech, UC Davis, and Arizona State University. And together we're working on using bio-based ground improvement techniques like you can see in the picture there. And looking at the geological causes of geohazards, and we've done a considerable amount of work in offshore wind. None of this is going to be presented in detail today. We had hoped to present this at a face-to-face seminar a couple of weeks ago, but unfortunately we had to cancel it due to COVID. But just some examples here, Mark and myself and Andy Wheeler in UCC have been looking at developing constraint maps for the Irish Sea with respect to offshore wind development, looking at new offshore site investigation techniques. And the project on the right-hand side is a collaboration between Jennifer Keenahan and UCD and Mark Cullen, again, looking at scar around offshore structures using computational fluid dynamics. And just a few examples of some of the projects we completed in iCRAG1. Top left, we developed a toolkit for imaging karst features with a particular aspect in relation to road projects. On the upper right there, this project was mentioned by Marie earlier. If you had been listening to the earlier sessions, this is a very deep karst feature which was encountered in the investigation for the Galway Outer Ring Road, and that was investigated by Brian McCabe and his team in NUIG. And on the bottom left, another karst project carried out by Chris Bean and Hala Karbala Ali at Dias. And here they've been looking at deep water-filled karst features and how these can be mapped and traced using seismic techniques. And of course, their aim there is to mitigate against the sort of flooding events we see in the west of Ireland. If you want to know more details in any of those projects, there's publications in all of them, so please contact us and we can help you there. And just a couple of examples of some new areas that we're going to be looking at in the next couple of years. Brian McCabe and NUIG is about to start a project on building road embankments on Peat. And Mark, Colin, myself, and Dave Igoe and Trinity are going to be developing our Irish capability, hopefully in CPT and cone penetration testing, which is the key site investigation tool for use in engineering offshore design. And the last talk in this session, and a very important talk in this session, is going to be by Quentin Crowley of TCD. And Quentin is going to address iCRAG's Earth Science and Society remit. And of course, we desire to embed iCRAG's Earth Science Society remit in all of our research areas. And hopefully we're going to show how these geotechnics and geohazards projects can better engage with stakeholders in local communities and how we can develop strategies to support decision making. So thank you very much for your attention. And that was a very quick overview. And please come back to me if you have any queries or need further details in any of those projects. Okay, so I'm going to hand over to Zili now. I think Zili is going to do the first detailed presentation.
Zili, if you can come up on stage, that would be great. And if you can share your screen as well, Zili, thank you.
Sure. Good afternoon, everyone. Can everyone see my screen now?
Yes, Zili, yeah.
Okay, let's kick off. So, good afternoon, everyone. My name is Zili Li. I'm a lecturer in geotechnics at University College Cork. Today, let me give you a short presentation about big data acquisition and machine learning-based assessment for underground infrastructure. Nowadays, many people talk about big data. So what would be big data in geoengineering? In my mind, there are many different categories and many different types. And there are two main types. One is structural data, which means that deformation measurements, movement, groundwater level, those data can be directly used for geo-asset assessment. The other type would be unstructured data, like image data, video data, and those data, we need to interpret them, convert them for geotechnical asset assessment. In the interest of time, in today's presentation, let's focus on big data acquisition, only for structural health monitoring and assessment of underground infrastructures, including tunnel, retaining wall, cavern, and etc. And then let's look at two examples of emerging monitoring tools. One is wireless sensor network to acquire deformation big data in real time. And the other is ultimate image data acquisition and assessment for unstructured image data. So now let's go to the first technology monitoring tool, wireless sensor network. Nowadays, wireless sensor network has been widely used for different types of geotechnical asset monitoring, including tunnels. Here, let me show you one example. One case study, we used wireless sensor network for Dublin Port Tunnel. Dublin Port Tunnel was built more than 15 years ago in 2006. And in this old tunnel, we have seen many different types of, let's say, structural defects. For example, concrete cracks, water leakage, and concrete spoiling, etc. To monitor the long-term tunnel deterioration, we can deploy wireless sensors. And those sensors, they can communicate between each other and send the data to a gateway. Eventually, the data will be sent via mobile network to our desktop. In Dublin Port Tunnel, one location of particular interest would be a cross passage. Here you can see that it's an illustration of the cross passage. It's the southbound of Dublin Port Tunnel, and this is the northbound. And in between, we have a cross passage for emergency evacuation. And at this critical cross passage, we deployed our wireless sensor network at 4 sections, at 4 rings. Ring 1, ring 2, ring 3, and ring 4. From the field measurements, we can see that the tunnel is still deforming with time, even 15 years after construction. So you can see that, let's say, not only the general trend, but if you pay attention to the details, you can see the deformation, tunnel deformation, it fluctuates with time. So here it gives you example that the real-time data, the big data, can bring us some new insights into the long-term tunnel behavior, long-term geostructural behavior than previously available by conventional methods. Now let's talk about the second emerging monitoring tool, automated image data acquisition. So, because in practice, not only crack and deterioration is not only observed at one location, but also at many other locations along a geo infrastructure. And to understand the tunnel behavior, the large-scale tunnel behavior, we need to gather a lot of data, a lot of image data. And we can gather the image data by a robot. For example, in this picture, you can see that it's a robot at CERN. And also, we can use drone to gather video data, image data. And for each individual image, each photo, we can automatically detect the cracks, the defects in this photo. And if we have many photos together, we can stitch those images together to get a long panorama, to get a 3D model. Based upon this long panorama, then let's look at the crack, the defects, section by section. So if we use machine learning algorithm to scan this long panorama, section by section, mileage by mileage, we can somehow get a crack percentage, crack density along the meter mileage, along the chainage. And this crack percentage can be used as an indicator for tunnel condition assessment. For example, in this central long panorama, we can see that the crack density, it varies along the longitudinal direction. And then if the crack density above a certain threshold, which suggests that this tunnel section deserves immediate, let's say, repair work. So in today's presentation, I introduced you 2 emerging monitoring tools. One is wireless sensor network for real-time big deformation data, and the other is automated image data acquisition for unstructured image data. And those 2 technologies and other emerging monitoring tools can be used in a variety of geotechnical, geological areas, including mines, quarries, cave, geological engineering, geoheritage, and etc. At last, I would like to say a big thank you to my collaborators and funding agencies. Thanks a lot for your attention.
Thank you very much, Zili. Can I ask Eileen to come up to the stage next? Zili, if you could leave, that would be great. If people have questions for Zili, please feel free to put them in the chat or contact him directly. And there's also an opportunity for networking later on this afternoon as well. Thanks, Eileen.
Thanks, Aoife. Hello, my name is Eileen McCarthy, and I'm going to be talking about peat stability on upland sites today. And just a call out to funding and support. So spoke funding, academic, industry partners, Finley, Temne and SSC, and various instrumentation services provided by various bodies. And who are we as a team? So we have 3 people in UCC and 1 in UCD. Myself, Amelia Pelenius, Ed Jarvis, and Mike Long in UCD. And I guess a key component of this is that between us, we have about 50 years of consultancy experience, but also more than 50 years of academic experience. So why is this research needed? Well, mass movement failure events keep happening, and they occur in areas designated as low probability of risk. Designated as low probability of risk by consultants to a degree still, and also in some cases by the vulnerability mapping at a national scale. So we're trying to figure out what's going on here and try to explain this. This became very evident last year where 3 major slides occurred. The first happened in June 2020, Shas Jump Kieran, Peat slide in County Leitrim, before and after. The second happened on the 13th of November, Neenbog Peat slide, County Donegal, before and after. And the next day, a third peat slide happened in County Kerry in Mount Eagle, and before and after. So in terms of research and development, we've developed and improved techniques and methodology of peat investigation. So approaching this from an organic soil point of view rather than traditional geotechnical mineral subsoil point of view. And getting down to the nuts and bolts of it, it is our opinion that peat is not characterized correctly in the field and needs much better logging that's currently being undertaken. So peat depths only, like probe depths with some KPA values from shear vein tests, is inadequate and suitable for hazard identification and risk assessment. Peat logging as per British Standard 5930, which is kind of the engineering standard for characterization, is better, but very limited. It was never really developed for peat, and capability was added on at the end, really. And the von Post humidification system is, we've done a lot of sensitivity tests on this, and it does give good indicator of likely strength and behavior, but it really should always be done in the field with fibre percentage content. And this is really good at separating out disturbed ground, i.e. modified ground, from intact ground. And we've done a lot of work on this, empirical studies, and the ranking of what we found the best parameters of the von Post with fibre, colour, degrees of saturation. And then we developed these simple field tests in terms of tensile compressive strength and then fibre orientation. So improved peat characterization. So logs like these, when they're done, to this level, are a very good indication of the likely water content, shear wave velocity, and strength of the ground and hydro units. So in this example, we've got 5 units, and we're picking these up nicely here in the in situ vertical profile testing, so the moisture content and shear wave velocity. And the added components of it, we're picking up in inflow areas in the blue here, and this is clearly indicating an increase in moisture content and a decrease in shear strength. And also in terms of the kind of the peat facies, if you want to call it, logging, we've got wood lignal fragments here, but both have high moisture content, but also a little spike in shear strength. So that kind of characterization is very good. And if you combine that with your geophysical spatial surveys, or radar picking up your layers, this is 80 megahertz survey. This gives you kind of the spatial component of your survey, which is very important, and shear string zonation of the previous plots. So we feel this gives appropriate assessment. Another area which we've worked on is improving the understanding of upland blanket bog hydrogeology over a range of ground conditions and land use. So we've been looking at a range of ground conditions. So in this case, illustrating a sloping flank upper to mid catchment. And we've got a sheet pile pseudo cofferdam construction methodology down here. And if you look again at these moisture content shear wave plots, you can see that we've got different signature types along the spatial context. So further away, less impacted, we got this kind of open signature type versus the more interaction and interweaving of the plots indicating disturbed conditions. In other areas, we've looked at a lot of hydrometric and chemistry, and these are just simplified kind of conceptuals of that. So you've got a full mitigation situation where no ground excavation was undertaken, it's driven pile foundation. You're maintaining the acrotem function in terms of hydrogeology, and these are all the piezometric levels of various horizons. And again, if you compare that to your sloping conditions in the baseline in terms of excavation, partial mitigation, again, there is a varying level of degree of mitigation there, but it is impacting on it. And I guess the one thing is drainage. You know, interceptor drain of this magnitude has a huge impact on your hydraulics. So the role of land use. So land use has always been known to be a major issue in peatland hydrogeology, ecohydrology, and geotechnical. But really, from the results of our research, and particularly what's happened over the last year or two, it is a factor that has to be prioritized in risk assessment. And I think the best example of this, if we go to that third landslide in Kerry last year, if you look at the spatial context of the hydrogeology flow, so we've got zone A, B, and C. So we've got a relatively intact diffuse overland sheet flow. So some in the aquitum, the upper layer, but quite readily diffuse flow over this kind of catchment. And this B boundary is really important. And this is where you have a flow regime change from this diffuse to this channelized and lineament discharge. So you're concentrated in at that point. And then obviously the fully modified section within the conifer plantation. Again, let's zoom in that. So we have a progression of peat slides happening at this site from left to right historically. And if you focus in on the red polygon area and look at the survey, we've got a series of vertical slumps developing along this disturbed outer B zone. And if you go to outer B zone here and inner, so these are the same vertical series of slumps, and you can see it's a displacement just using metrics in my hand. So vertically 40 to 50 centimeters, 30 across. And then right in the inner zone, there's been denudation and cracking, and water is getting into the subsurface at this point. And now it's become, you know, a buoyancy layer and causing instability underneath the base of the peat. So we've developed these suitable models for peatland evaluation for risk assessment, for hazards, for upland blanket bogs in the context of renewables. But we'd now like to test our methodology assessment on other peatlands over a range of applications. So all peatlands, so cover the upland blanket bogs, but lowland blanket bogs also, we'd like to look at that, raised bogs and fens for different objectives. So we've done the risk avoidance mitigation, but it's also the asset management. There's a lot of these sites all over the country, and we need to look at it now in terms of land use, contrast, boundary conditions. There's biodiversity conservation, again at that zone, and peatland rehabilitation restoration. And then for a variety of land use conditions, both historic and planned. So your conservation sites, your infrastructure, renewables, conifer plantations particularly, and peat harvesting historic. And I guess that feeds into the rehabilitation restoration programs, where we're trying to reverse, you know, the timelines of impact, you know, in terms of hydrogeology. So I suppose to apply what we've learned to those. So I'd like to thank you for listening. And if you want to contact me to discuss this topic further, my details there, Eileen McCarthy at ucc.ie.
Thank you very much, Eileen. That was very interesting. And again, if anyone has any questions for Eileen, to please post them in the chat or contact her directly, as she said. Next up, we have Andy Trafford, who's going to give us a short presentation on fibre optic approach for offshore site investigations. So Andy, thank you for coming up on stage. And if you can share your screen now, please. That's perfect. Thanks very much.
Okay. Hi, my name's Andy Trafford. Excuse me. I'm a researcher with iCRAG. And I've been working with Shane Donahue in School of Civil Engineering, UCD, and also Rob Elwood with our industry partner, OptiSense. And I just want to going to talk to you about the research we're doing in use of fibre optics in offshore site investigation. And this is probably most relevant at the moment for the development of offshore wind. So if I just quickly go into what it is we use, the techniques. We use a technique called distributed acoustic sensing. When a sound wave passes a fibre optic cable, it causes minute strain within the glass fibre. And these are detected by the DAS system, the distributed acoustic sensing system, in the form of backscattered light. So essentially what we're using is an invisible laser light to listen to inaudible sound and we use this to determine the stiffness of the subsurface. So it's quite clever stuff. So where we started, we have 3 trial locations. Well, we started at Blessington Sands Quarry. We moved to an intertidal zone in Dollymount Strand, and then we had offshore trials taking place in Dundalk Bay. So we've used the lessons we learned at each step in trying to fine-tune a methodology so we could use it in the offshore environment. We chose Dollymount Strand as a test site, mainly because it's a wide intertidal zone. So this means that we can survey the same portion of the subsurface at high water using a marine approach, but also at low water using a more traditional terrestrial approach. So it gives us some correlation between the two different methods at the same location. How we go about this, we install a cable, standard fibre optic cable. In this case, we put it a kilometre out from the beachhead using a small vessel, and then we used a second boat as a gunboat, and we used an air gun for the source. If we just have a look at some of the data from the DAS system, it varies from the traditional seismics in that we record continuously. This is a speeded up version of a 20-minute duration of DAS data. And what we're looking at there is a 1,000-metre long cable, 900 metres underwater, and 100 metres on the right-hand side, which is at the beachhead. The horizontal features you can see there are all individual shots taken offshore. And also what you can see is we can see these diagonal features, these sloping features, and these are waves travelling towards the beach. And the data on the right-hand side is 100 metres on the beach. If we have a look at if we just have a look at the data in basically in real time, on the right-hand side, you can see the individual footfall from people on the beach. And then round about the centre of the cable, at about 500 metres, this is an air gun shot. And the high amplitudes that you can see fanning out from that centre are the Schultz wave or the surface wave. And that's the bit of information which we are keen on, that we have to analyse. So once we isolate that, we can produce a typical shot record where we have time series data, and we can see there quite clearly the surface wave response. In March this year, we were lucky enough to get 10 days ship time on the Celtic Voyager, and I think this highlights how iCRAG really works in practice. There's a lot of collaboration, and what we have equipment coming in and expertise and different inputs. We've got ocean bottom sensors and pressure sensors from DIAS. We've got gravity cores and positional data from the Marine Institute, Sparker systems from the Geological Survey, and then we've got our industry partner who provide all the fibre optic hardware, and all that is comes together offshore. And you can see from the schematic there's a lot of things that have to actually occur, but because we have this excellent research platform on board the vessel, we can carry out very high level research. We have the skills and the expertise to bring everything together. Thank you.
Thank you very much, Andy. That was really good. Again, if there's any questions for Andy, please contact him directly or at the end of the session. Andy, if you can just leave the stage, that would be great. I'm going to hand over to David now to present on geotechnical research for foundation design. So David, if you want to share your screen.
Sure, yeah. Let's do that now. So you should be able to see that okay, hopefully.
That's perfect. That's good.
So my name is David Igoe. I'm an assistant professor in Trinity College Dublin, and my talk today is on geotechnical research for offshore foundation design. So I'm going to focus on a few different projects. The first one is called the PISA project, or pile soil analysis, and it's to do with the design of offshore foundations for wind turbines. So wind turbines, more than 80% of wind turbines are founded on monopile foundations. And this is a project to essentially develop new design methods which are used for offshore monopiles. So the project was led by Dong Energy, who are now renamed to Ørsted, who are the largest developer of offshore wind in the world. And it was funded through the UK Carbon Trust Offshore Wind Accelerator Programme. So the academic work group who was steering the direction of the project was led by Oxford, Imperial College and UCD, where I was working at the time. So the project had a total budget of $3.5 million and was completed in 2016. As I said, the project aim was to develop new design methods for laterally loaded piles, which are to be used in the offshore wind industry. And up until this project, monopiles were designed using industry methods from the oil and gas industry, which have quite different geometries. So an oil and gas pile is typically quite small in diameter and quite long. Whereas an offshore monopile is very large diameter, maybe up to 10 meters in diameter, and quite short relative to an oil and gas pile. So the methods used up until this project were quite unsuitable for these geometries, and there was a very big need to develop a new method for the project. So this was done using a campaign of monopile field tests and also some 3D FE modeling, which was undertaken to develop the new method. So just looking at the field tests, 2 test sites were chosen. One, a Cowden test site in the north of England near Hull, which is a stiff glacial till site. And there was also a dense marine sand site in the north of France, in Dunkirk. And these were chosen based on their soil properties that were similar to typical offshore wind conditions, offshore wind properties in the North Sea. So the photo here in the middle of the photos here from the top in the center show large 2-meter diameter monopiles from the Cowden test site, and at the bottom is from the Dunkirk test site. And these piles are being laterally loaded, so they're being pulled together with these very large hydraulic rams. So we're applying very large lateral loads and monitoring the response. So each of these tests had more than 100 instruments involved. We monitored strains, groundwater pressures, rotations of the pile above and below ground level. So they were very complex set of tests that were undertaken. And the figure on the right here shows the response of the field tests in the black line. So it's a load displacement curve. So on the y-axis is the force that's being applied, and the x-axis is the displacement. And we see the field test data is the solid line and shows quite a large capacity. Some 3D FE modeling is the dashed line that was done by Imperial College to predict the field test response, and we get a very good match with the 3D FE model. The industry standard methods that were used were very conservative. They were typically under predicting the capacity by more than a factor of 2. Develop, you can save up to 30% on the steel weight on monopiles, so it's a huge saving that can be achieved. So this project, as I mentioned, has been very successful. It is now the de facto design approach that's used by engineers designing monopiles. So in Europe, if you're designing a monopile, you're more than likely using this PISA design approach. On the right-hand side here, we show it's kind of the design approach that was developed. So essentially, a lot of 3D FE models were undertaken. The soil reaction curves were extracted from those 3D FE models and applied in a simple beam spring model, as shown in the bottom left-hand corner here. So this beam spring model allows the engineer to run many hundreds or thousands of calculations if required very quickly. So each beam spring model can be run in a matter of seconds, compared to a full 3D FE analysis, which will take several hours to set up and several hours to run. So essentially what we have is a method that's very quick to run, but it's also has very similar accuracy to the full 3D FE method. The scientific results from this project were published last year in 2020 in a special issue of the Geotechnical, which is the world's premier journal in geotechnical engineering. And it's the first time in 30 years there's been a special issue related to one project. So this was a very big achievement. The project also won the British Geotechnical Association Fleming Award for Best Project in 2019. And one of the papers published last year won the BGA Gold Medal for Best Paper in 2020. So it was a huge achievement. So looking, just briefly talking about some other projects that are ongoing at the moment that I'm leading. The first one is on jacket pile design and looking at pile aging in sands. So this is funded by the Geological Survey under the short call. And essentially what we're doing is we're looking at how the vertical capacity of piles change over time. So we've done some field tests where we've driven piles into our test site in Blessington. So it's a dense sand test site. And then we measure the pile capacity in tension. So we set up a load frame like shown here on the right, and we essentially apply a vertical load and we pull the piles out of the ground and we measure the shaft capacity on the piles. And we do this at different time intervals on different piles. And we're trying to establish characteristics of how the pile capacity changes over time. And this is a very important project for pile jacket structures, which are going to be used a lot in the offshore wind industry. Another project I want to discuss is an SCAI funded project on developing the damping parameters for Irish offshore wind farms. For this project, essentially what we're doing is we're performing an advanced suite of cyclic triaxial testing, and we're measuring the soil damping for a range of soil types relevant to the Irish offshore wind sector. So we use the results from the lab element tests, and we apply what we know from these to develop constitutive models, to calibrate constitutive models that can capture hysteresis and damping. And we undertake 3D FE analysis of full monopile sections, so we can understand how, from a soil element up into a full monopile, how the different behavior is dominated by damping. And the idea behind this project will be to develop simple design tools and design charts which can be used by engineers for various stages of design. So this project is due to be completed at the end of 2022. And a final project, which I've just received word has been funded, is an EPSRC SFI funded study called RoboCone. And this is to do with developing new design tools for ground investigation. So it's essentially advancing the industry standard cone penetration test, but adding more advanced intelligent robotics, essentially to undertake a number of different tests in the soil, so we can model more complex behavior, look at things like cyclic loading, aging, all these aspects. So this is a project which will be starting in February in 2022. So we're very excited about this. So just to acknowledge some funding partners: iCRAG, SCAI, IRC, and GSI, as well as Roadstone, who've provided our test site, and Lloyd's Acoustics, Toronto Piling, Tear Dry Piling, and In Situ SI, who have all helped greatly with our research. So thanks everybody for listening, and for any questions, please contact the email there below, igoe@tcd.ie. Thanks everyone.
Thanks very much, David. David just joined iCRAG this year, and we're very welcome to the centre this year, and looking forward to working with him over the next phase. I'm going to ask Maria Judge next to come on stage, and Maria is going to speak about our US Ireland Centre to Centre partnership, and this is in collaboration with the NSF funded Centre for Biomediated and Bio-inspired Geotechnics and Queen's University Belfast Energy Efficient Materials Research Centre, and with several Irish and international partners. So Maria, I will go over to you. Can you share your screen?
Good, thank you. Okay, so you should be able to see the screen now.
Can you just put it into screen mode, Maria?
There we go. How's that? Okay,
yeah,
great. So yeah, my name is Maria Judge. I'm a researcher based in the School of Engineering at UCD. My supervisor is Dr. Mike Long, and I'm working on the US Ireland Centre to Centre collaboration C2C. So on behalf of other project partners, I'll give an overview today on how we go about investigating bio-based mineral precipitation for ground improvement and stabilisation. So the US Ireland Centre to Centre collaboration is funded under the US Ireland Research Scheme. The title of the project is Multi-Scale Investigation of Bio-Based Mineral Precipitation in Carbonate-Bearing Granular Soils and Constructed Related Waste. Previous similar studies have looked at primarily quartz granular soils or sands. So altogether, involved in the collaboration, there are 3 centres: iCRAG in Ireland, the Centre for Biomediated and Bio-Inspired Geotechnics, CBBG, in the US, and the Energy Efficient Materials Research Centre, EEM, in Northern Ireland. There are 5 universities. UCD is part of iCRAG, Arizona State University, University of California in Davis, and the Georgia Institute of Technology under CBBG, and Queen's University Belfast under EEM. So we also have 7 active industry members as well. So we go about the development of improved bio-cementation methods and studying these primarily to increase soil shear strength and stiffness, for ground improvements and stabilization, for slope stability and minimizing landsliding in weak soils, for hazardous waste encapsulation such as asbestos, and the reduction in use of Portland cement. There's an example here of field scale trials from the Netherlands as well that is looking at using bio-cementation for borehole stabilization. There's also an infographic on the right-hand side that shows additional suggested applications for ureilitic biomineralization, and that has been published by Phillips et al. In 2013. So investigating bio-based mineral precipitation, and in doing so we use 2 different approaches. We use the MICP method and the EICP method. So for MICP, microbially induced carbonate precipitation involves a bacteria known as Sporoarcina pasteurii, and these produce urease enzymes that are used to catalyze the hydrolysis of urea. They're pictured on the top right-hand side of the screen. Whereas for EICP, or enzyme-induced carbonate precipitation, plant-produced urease enzymes are used for urolysis. These come from the jack bean plant, which is rich in urease. Also, during the process, calcium chloride is added as an additional Ca source in solution, and ammonia is produced as a byproduct. So at the initial stage of the project, a quaternary site was selected at Blessington, County Wicklow. It is known to have a carbonate-bearing material. The material is part of quaternary glacial lacustrine sedimentary deposit. Some on-site geophysics and borehole analysis helped target the optimum soil for further study and trials. The samples were retrieved from the quarry and disseminated to project partners for further laboratory analysis. Geotechnical, geochemical, geophysical, and geological analysis on the material and its properties were undertaken prior to EICP or MICP. The table here shows a summary of the geotechnical characteristics of the material found in 4 different universities. And there are 2 images inset here. One is petrographic mineralogical analysis showing that the sample comprises lithic fragments of quartz and carbonates, mica, feldspar, iron, and iron oxides. Whereas the SEM image on the top right-hand corner shows that the granular particles themselves are subrounded to subangular lithic fragments. The provenance is the Leinster granite and the Dublin limestone, and they have very varied surface textures, which should have an implication during the cementation phase. So we're also looking at analysing the groundwater geochemistry of the area, and of course the native bacteria in the soils themselves. So we're also now currently moving on to the testing phase. Some lab column MICP tests have been conducted already and they are ongoing. Photographed here in the centre of the screen is an example of MICP column testing being carried out in Georgia Tech. And the images on the right-hand side of the screen show an SEM image of a grain of the material before and during cementation. So you can see some carbonate cement forming on the grain itself. And just the image on the bottom right-hand corner then shows that carbonate cement in more detail. So the project aims to produce potential applications for EICP and MICP for sustainable engineering in carbonate-bearing soils, and it will also produce recommendations for future research. So that is the C2C project, and I will leave it there. Thank you for
Maria, that's very interesting. And if anybody has any questions or would like to hear more, please feel free to contact Maria and also Mike, and they can give you more detail on the project. And finally, our last speaker is Quentin Crowley from TCD. And as you've already heard from the industry panel, proof of concept is usually important and is embedded across the iCRAG. And so this evening, Quentin is going to speak to us about increasing stakeholder engagement for geotechnical and geohazard projects. So Quentin, if you want to share your screen.
Yeah, I'm just attempting to do this now. Please bear with me a second.
Yeah, no problem.
And
yeah. And if you just want to put into presentation mode, if you can.
Yeah, I'm just attempting this now, 1 second. Excellent, so starting slide. Hi everybody, and thank you for sticking with us. My name is Quentin Crowley. I'm an associate professor in geology in Trinity College Dublin, and I'm joined in this presentation in co-authorship with my colleague David Heavey, who is also at Trinity College, professor at the School of Psychology. And as Aoife mentioned, this short talk is on the topic of increasing stakeholder engagement, particularly for geotechnical and geohazard projects. So by way of introduction, as I'm sure you'll agree, for most projects, stakeholder engagement is really crucial, and this is especially the case for geotechnical and geohazard projects. Within these projects, there are often difficulties in gaining support from local communities, or perhaps in recruiting participants where this may be required. So what David and I we bring our expertise in geoscience and psychology to really drill down and address these challenges in order to build trust and buy-in from communities for these project successes. But not only that, we take a structured systems approach to identify and work with different levels of stakeholders within these systems in order to primarily support sustainable development of cities and communities. By way of a little bit of background, David and I collaborated on a project in the first phase of iCRAG, which was focused on gaining a better understanding of stakeholder risk perception in relation to radon. So radon is a gas, it's geogenic in origin. It happens to be the second highest cause of lung cancer globally after tobacco smoking. And in the context of Ireland, about 300 lung cancer cases are related to radon exposure in people's homes every single year. So this is a big challenge nationally and globally, yet pretty much universally, there is reluctance to test for radon, and where remediation to lower concentrations of radon in homes is necessary, there's also a very low uptake of this as well. So our project, which was in collaboration with a postdoctoral researcher, Gary Bradley, we mentored, discovered a number of things, two of which I'll highlight here. One is there tends to be an optimistic bias where individuals feel the risk applies to others and not to them, which of course cannot be the case in every instance. And sometimes there is an element of stigma where individuals do not want to be identified within their communities as somebody who has an issue with high radon. So we're able to adopt these and integrate these insights from a psychology perspective into changing the messaging to improve the uptake of radon testing and remediation. So moving forward and looking to the next phase of iCRAG, this is a short case study we heard from Eileen McCarthy earlier on her excellent presentation on developing renewable energy on upland sites, and particularly the risks of landslides and subsidence within these sites. So what I've done here is in the center of the slide, you'll see there are 3 different stakeholder groups mentioned: developers, public nearby the installations or the developments, and the landowners on whose land the development is actually taking place. Then on the left-hand side of the slide are risks or perceived risks or aspects which may contribute to a negative sentiment. And on the opposite side on the right are attributes which may contribute to a positive sentiment. Now, if you focus on the middle of the slide and look at the public nearby, it is true to say in Ireland and in countries, other countries, that there is some aspect of positive sentiment in relation to these kinds of developments in upland sites, but overwhelmingly, and particularly in Ireland, the sentiment of public nearby this kind of development is negative. And various reasons are cited for this. Individual stakeholders may mention electromagnetic radiation, nuisance of blade flicker or noise, or perhaps landscape change and loss of some kind of cultural heritage within this landscape change. The landowners, on the other hand, tend to be overwhelmingly positive in their sentiment and attitudes towards these kind of installations. So they may view these as adding some kind of recreational value to the landscape, as we see in the Galway Park. But importantly, this makes some kind of financial security for the farmers or landowners, and they see this as good use of their marginal land. Importantly, the local landowners tend to have a very good understanding of the local landscape and have good knowledge of historical subsidence or landslides. So what are the possible considerations and insights that we can gain from this kind of case study? Well, it's pretty plain to see that communities are defined by geography or in some other way. We know that communities have histories. Often there is some kind of embedded narrative or some shared recollection of previous events. And this can be in a positive or in a negative sense. Certainly, there is a level of complexity and structure within communities, particularly in relation to decision makers and influencers within these communities. So what I want to highlight here is that our approach really is to move away from thinking of individual stakeholders and instead to apply a very structured systems approach to better understand different motivations, perceptions, and interactions within this system of stakeholders. So through a process of appropriate consultation and listening, we wish or we aspire to connect decision makers into a process which will connect locally and build upwards within the communities. So for listeners in Ireland, you will have heard of Teagasc. Teagasc is Ireland's Agricultural and Food Development Authority. And if I can give an example of this kind of stakeholder engagement, which Teagasc has been employing for many years, Teagasc run these things called demonstration farms. And these demonstration farms specifically identify key stakeholders within existing, in this case, farming communities. So these farmers are usually trusted voices within their communities. They're quite often early adopters of technology. And they're certainly influencers in that they're well respected, and they are members of farming co-ops. These co-ops themselves operate at a range of different scales, from local farms to regional basis or a national network. And really, Teagasc, through these demonstration farms, build relationships and demonstrate benefits of interventions. So we see value in this kind of structured systems type approach, in that the benefit is in bringing all of the key agents along on the stakeholder journey. So just to finish off, you may have noticed that there is one presentation on the subject of earth science and society within the different breakout sessions. So really, we wish to firmly embed the ethos of iCRAG's earth science and society in all targeted research areas. I would say that David and I are very open to co-create complementary projects with you, which would utilize our kind of structured systems approach to projects which would benefit from understanding stakeholder perceptions, motivations, and reactions, whereby an approach to engage local communities in a way that is most mutually beneficial and sensitive to local needs is needed, and where you might like to develop strategies to support responsible and participatory decision-making. If you wish to know more, please email me, crowleyq@tcd.ie, or we can chat in the networking session later on. So thank you very much for your attention.
Thank you very much, Quentin. That was very interesting. I just want to say thank you to all our speakers, Mike, Zili, Eileen, Andy, David, Maria, and Quentin, and David Hebe also for his contribution to the presentation. We have ran over time. The final keynote speech is going on live now on the stage. So unfortunately, we don't have time for questions, but I really would encourage people to please contact the researchers or to please contact myself or Emer if you want to get in contact with any of the researchers. And again, so please, if you can make it to the networking event this evening, please do, as there will be a breakout session or a room for the Geohazards Geoengineering group. So if you have any questions, you can approach the researchers directly there. Thank you very much. And I would ask everyone to make